Here in section 6.3 we look at solving trigonometric equations. This time we're looking at equations that involve input angles that are half angles and multiple of angles. For example, let's say cosine of 2 theta. When we look at cosine of 2 theta, we have a multiple of the angle theta. So cosine of 2 theta, this is what we would also call it a double angle. But when we're solving for cosine in this type of situation, I want to keep in mind that I am not allowed to cancel a number on the outside with a number that's on the inside of the angle. So this is my input angle. I'm not allowed to change the input angle by dividing or canceling with something that's on the outside of the function. So I want to make sure that we don't do that. So cosine of 2 theta divided by 2 does not give us cosine theta. So we want to be careful that the input angle is not something that we're going to change or divide out by. So that is important as we go forward because we need to know how do we deal with cosine of 2 theta or cosine of 3 theta or cosine of theta divided by 2 when it's part of the input angle. What we're going to do when we solve for multiple angles is we are going to adjust solution intervals or use identities. So the steps that we're going to use to solve using adjusted solution intervals is the first thing we're going to do is something similar we did in the last section for section 6.2. We want to first get the trig function and its angle by itself on one side. So we want cosine of whatever the angle is equals, and then we want a number on the other side. That's our goal. The next thing we're going to do is we're going to solve for the input angle. So n times theta. And remember, n here is just representing any integer. So we're going to solve for n theta first within the adjusted solution interval. We'll talk about that in just a minute. Then we actually want to solve for theta. The whole goal here in the end is to know what theta has to be. What does theta itself have to be in order to balance out the equation? So we solve for n theta first, and then we make sure that we divide by n so that we actually solve for theta itself. So what does it mean to adjust solution intervals? Well, in order to solve for the angle theta, we're usually given a particular interval that we want our answers for theta to be within. So let's say that we are asked to eventually solve for theta, to solve for that unknown angle theta between 0 and 360 degrees. We have less than or equal to or less than. Less than or equal to means 0 is an allowed value for theta, and 360 itself is not an allowed value for theta. But in order to solve for theta between the given interval, we would have to first solve for n theta between an adjusted interval. So basically we go through and multiply everything through by n. Then we have n theta between two particular values. And we first solve for n theta between those two particular values. Why would we do that? Well, then I'm going to go through, and once I have solved for n theta first, then I'm going to go through and divide everything through by n. When everything is divided by n, suddenly we have solved for theta in between the two desired values within the original desired interval domain. So for example, if we are solving an equation that contains an input angle of 2 theta, remember that we really want to get to what is the value for theta. And if we originally asked to solve for theta between 0 and 360 degrees, then we must first solve for 2 theta between 0 and 720 degrees. So first we solve for 2 theta. That's going to be our first step, solve for 2 theta. I'm going to solve for 2 theta. I'm going to take my original interval and multiply everything through by 2. So we solve for 2 theta between 0 and 720. So we multiply everything through by 2. First we solve for 2 theta. Then, remember the goal is to really get to 2 theta. So we're going to divide everything through by 2. and we divide everything through by 2, suddenly we have theta within the desired original interval. So if we are asked to solve for half theta, or theta divided by 2, and we are asked to solve for theta itself between 0 and 360, when we are first solving for theta over 2, we're going to go through and we're going to divide everything through by 2. So we only solve for theta over 2, or half theta, between 0 and 180 degrees. What we're going to do to actually get to theta is multiply everything through by 2. And when we do that, we get back to the original interval for theta. This is what we call adjusting our solution intervals. If the equation that we are trying to solve contains an input angle of 3 theta, and we actually want to solve for theta itself between 0 and 360, then we must adjust our solution interval to first solve for 3 theta. And when we solve for 3 theta at first, we have to go through and we're going to multiply everything through by 3. So 3 times 0 theta would be 0 degrees, 3 times 0 degrees is 0 degrees. Less than or equal to, and that would be 3 times theta. Less than, and 3 times 360 would be 1080 degrees, or 1080 degrees. So we will first adjust the solution interval to solve for 3 theta between 0 and 1080. Why would we do that first? Well, if we solve for 3 theta between 0 and 1080, what we'll eventually do is we'll divide everything through by 3, and when we do that, we will have solved for theta between 0 and 360. For example 1, we are asked to solve for theta in the equation cosine of 2 theta is equal to square root of 3 divided by 2. First, we want to notice that the input angle for cosine is 2 theta. This is our input angle. And we cannot change it by dividing both sides by 2. We just have to deal with this 2 theta. So when we're solving equations that deal with multiple angles, or some number times theta on the input of our function, first thing you want to do is get cosine of the multiple angle by itself. So cosine of the angle. And in this particular equation, that is already done. So we have cosine 2 theta by itself, and then on the other side we have our number square root of 3 divided by 2. We're going to solve for n theta, so we want to figure out 2 theta. We want to solve for that input angle. What does the angle 2 theta have to be? So whatever the original angle is, that 2 theta, we're going to put that angle on one side by itself, and we're going to say, we're going to solve for 2 theta between what? Well, the original value of theta, eventually what we want to get to is theta itself between 0 and 360. So we first solve for n theta, or 2 theta, between, we're going to multiply everything through by 2. And multiply 0 by 2, I get 0. Multiply theta by 2, I get 2 theta. Multiply 360 by 2, we get 720. So we're going to solve for 2 theta, basically 2 rotations around the circle. So what angles would have a cosine value of square root of 3 over 2? And it's a positive value, so we're looking in quadrant 1 and in quadrant 4, since cosine is positive in those 2 quadrants. And the square root of 3 over 2, that's our 30-degree angle family. So 30 degrees in quadrant 1, 330 degrees in quadrant 4. So we have 2 values going from once around the circle. We have 30 degrees and 330 degrees. And this is from one rotation around the circle. That's from 0 to 360. Well, we're asked to go for 2 theta, we're asked to go twice around the circle from 0 to 720. So we're going to go around the circle again. So if I go one complete rotation and then 30 degrees more, so we're going to find a coterminal angle to 30 degrees. For the second time around the circle, we get 390 degrees for that second rotation. Now, notice that these 2 angles will be coterminal angles. One rotation around, second rotation around. 330, we want a coterminal angle to that one as well for the second time around the circle. So a coterminal to angle to that, we would add 360. We get 690 degrees. So we have solved for 2 theta, but keep in mind that this is not actually what we want to solve for in the end. What we really want to know is what does theta have to be in order to make this a true statement. So we're going to take our solutions and we're going to divide everything by 2. So we're going to divide by 2 and we're going to divide all of the solutions by 2 as well. So we're going to divide by whatever's in front of theta. So we get theta is equal to 30 divided by 2 is 15 degrees. 330 divided by 2 would be 165 degrees. 390 divided by 2, 195 degrees. 690 divided by 2, we get 345 degrees. Notice that the solutions that we have for theta are between 0 and 360 degrees. All 4 solutions are in the desired original interval for theta. I want to prove that these actually do work in the original equation so we can have a good picture and a good idea of what's really going on here. So what we're actually doing is we are solving for what angle theta we would need to put back into the original equation, multiply by 2. Once we find the cosine value of that double angle, it should be square root of 3 over 2. So one of our solutions was 15 degrees. So if I put 15 degrees back to the original equation, the first thing that has to happen is that you would have to multiply the angle by 2. So that's cosine of 30 degrees. Is cosine of 30 degrees positive square root of 3 over 2? And the answer is yes. So we get something that is balanced for both sides of the equation. Let's do it again. Let's do another one. Cosine of 2 times 165 degrees. So in order to check, we would first multiply the angle by 2. So we get cosine of 330 degrees. And cosine of 330 degrees, that's in quadrant 4, and that is also positive square root of 3 over 2. So we can see that it's going to work for all 4 of these angles. Let's try the next one, cosine of 2 theta. So what we're solving for, keep in mind, is we're solving for the angle that we would have to double first, then find the cosine value of it to make sure we get out the cosine value on the other side. Cosine of 2 times 195, that would be 390 degrees. And keep in mind that that is in quadrant 1, so it will be a positive value. And it is the 30-degree angle family, so that would be square root of 3 over 2. And we get an equation that's balanced. And let's look at the last one there. Cosine of 2 times the angle 345 should also give us positive square root of 3 over 2. So if we take that value for theta, 345 degrees, and we double it, that would give us cosine of, when we double that, we get 690 degrees. And we find a coterminal angle to that, of course. That would be coterminal to 330 degrees. So it comes from quadrant 4. That's our pi over 3, our 30-degree angle family from quadrant 4, which is square root of 3 over 2. So we're looking for the angle, we're on the hunt for the angle that we would have to double to get that cosine value of square root of 3 over 2. And we get 4 angles from 0 to 360 that if we double them and take the cosine value of them, we get square root of 3 over 2. We want to solve for x, and our equation is 3 times tangent of 3x is equal to square root of 3. First thing you want to do is you want to isolate the trig function and its angle. The input angle is 3x, so we want to get tangent of 3x by itself on one side. So in order to do that, we have to get rid of the 3 that's being multiplied times the front of the trig function. So we're going to divide both sides by 3. Since these 3's are both on the outside, they can cancel with each other, and so we're left with tangent of 3x is equal to square root of 3 divided by 3. Since we're solving an equation that deals with a multiple angle, so some number times the angle, the value x on the inside of the function, we want to consider the original domain. So what do the original solutions have to go between? Well, we're asked to solve for x between 0 radians, keep in mind we're talking about radians here, between 0 and 2 pi radians. So what we first must do is solve for the angle 3x with an adjusted interval. Well, we want to multiply all 3 parts of the original domain by 3. So if I multiply by 3, we get 0 less than or equal to 3x less than, and we have 2 pi times 3, which gives us 6 pi. What we're really looking for now basically is 3 times 2 theta would basically be 3 rotations around the circle. So 3 rotations around the unit circle. So the angle that we're referring to here, so we're solving for 3x. We want to know what does the input angle have to be. We want to know what angles are going to give us this tangent value of square root of 3 over 3. So what angle family, what reference angle family is this referring to? This is our 30-degree angle family, or because we're talking about radians, this is the pi over 6 family. So pi over 6, and it's a positive tangent value, so not only are we talking about the quadrant 1 angles, but also quadrant 3 angles, where tangent is also positive. And that would be 7 pi over 6. This is one rotation around the circle, and because we multiplied by 3, we're actually looking for 3 rotations around the circle. So we want to find a coterminal angle to pi over 6. In order to find coterminal angles, we add 2 pi. Now we're going to think about these as both fractions, so we're going to think about it as 2 pi over 1. So we have pi over 6 plus 2 pi over 1. We know that they have to have a common denominator of 6. So we multiply top and the bottom by 6. And that gives 12 pi over 6. So if my denominator is 6 and I want to find a coterminal angle, we will add 12 pi over 6. That's the same as adding 2 pi. So this angle, second time around the circle, for that second rotation, will be 13 pi, keeping the same denominator of 6. So we get 13 pi over 6, and this is the second rotation around the circle. And we want to find also a coterminal angle to 7 pi over 6. And we just said that in order to do that, we would have to add 2 pi. And we also said that we need to have a common denominator before we can actually add it, so we're going to add 12 pi over 6. So we add the numerators together, that gives 19 pi, keep the same denominator of 6. So we're going to do now a third rotation. So we're going to take the second rotation angles, and we are going to find a coterminal angle to those. We're going to add 2 pi, which with a common denominator, we're going to add 12 pi over 6. So 13 pi over 6 plus 12 pi over 6 gives us the third rotation angle. We get 25 pi divided by 6. We're going to do the same thing with 19 pi over 6. So when we added these two, we got 19 pi over 6. We want to add 2 pi again. We want to find a coterminal angle to that second rotation angle. So we're going to add 12 pi over 6 again. And when we add 19 plus 21, we get 31 pi. Keep the same denominator of 6. So here's coterminal angles for 3 times around the circle. So you want to keep in mind that pi over 6 is coterminal to 13 pi over 6, which is also coterminal to 25 pi over 6. Just different amounts of rotation around the circle. But they all are in the same exact location as pi over 6. 7 pi over 6 is coterminal to 19 pi over 6, and that's also coterminal to 31 pi over 6. So all of them are in this exact same spot as 7 pi over 6, just different amounts of rotation around the circle. Alright, so we solve for 3x. Now keep in mind that that's not where we want to stop. We actually want to solve for x itself. So to solve for x, we are going to divide everything through by 3. But dividing a fraction by 3 is the same thing as basically multiplying by 1/3. So I'm going to rewrite this, and I'm going to come down here and actually multiply everything through by 1/3. So I'm just going to come down here, and I'm going to rewrite this. So we have 3x is equal to, we had pi over 6, 7 pi over 6, 13 pi over 6, 19 pi over 6, 25 pi over 6, and 31 pi over 6. And to solve for x, we're going to multiply by 1/3. And we're going to do the same thing to both sides of this equation. We're going to multiply both sides by 1/3. The reason we're going to do that is multiplying by 1/3 is the same as dividing by 3. And we want that 3 to go away in front of the x. So we get x is equal to, now we're going to multiply each of these fractions by 1/3. Now if I multiply by 1/3, what's going to happen is that all of the denominators are going to get multiplied by 3, so all of the denominators are going to become 18. All the numerators are going to stay the same because when I multiply the top by 1, it stays the same. So we get pi over 18, 7 pi over 18, 13 pi over 18, 19 pi divided by 18, 25 pi divided by 18, and 31 pi divided by 18. And these are all solutions that, if I were to graph them, I would find would be x values, radian measures between 0 and 2 pi. In example 3, we're asked to solve the equation square root of 2 times sine of 3x minus 1 equals 0. And this one's a little bit different than the last ones because we are asked to solve for all solutions in radians. So we do not actually have an interval that x is required to be within. We're asked to solve for all possible solutions for x. So the first thing we want to do is get the trig function and its input angle by itself. So we want to isolate or get by itself sine 3x. In order to do that, we do adding and subtracting first, so we will add 1 to both sides. So we have the square root of 2 times sine of 3x equals 1, and then we will divide both sides by the square root of 2. And we're doing that because we are multiplying square root of 2 times sine of 3x. And when we do that, square root of 2's will cancel, and we're left with sine of 3x is equal to 1 over the square root of 2, which, of course, if we rationalize, would be square root of 2 divided by 2. Now, we do not have to adjust our solution intervals here because we don't have a specific solution for x, a specific interval that x must be within. We're solving for all possible solutions. So first we're going to describe 3x. What does the angle 3x have to be that if I take the sine of that angle, we get square root of 2 over 2? Well, that's our 45-degree angle family, or our pi over 4 family. Since we're working in radians, that's the pi over 4 family. And that's a positive value for sine, so pi over 4 in quadrant 1. And remember that we're looking for all possible solutions. So all possible coterminal solutions, we would add 2 pi in or 2 in pi, however we want to write that. And we also want to solve for the quadrant 2 solutions. And so in quadrant 2, we're talking about the pi over 4 family. That's 3 pi over 4 from quadrant 2. So sine also takes on that positive square root of 2 over 2 sine value in quadrant 2 at 3 pi over 4. And we're looking for all possible coterminal solutions, so we will add 2 pi in. So there's all possible solutions for 3x. But keep in mind that I don't want to solve just for 3x, we actually want to solve for x. So we're going to divide everything through by 3, which also, we said before, would be the same thing as multiplying everything through by 1/3. So I'm going to write this down again down here in this step below. So I'm going to rewrite. We have 3x equals pi over 4 plus 2 pi n, 3 pi over 4 plus 2 pi n. And something that's important, if I'm going to divide by 3 to get x by itself, that's the same thing as multiplying by 1/3. And what's important here is that I'm not just multiplying the original angles by 1/3, we're doing it to every part, every term on both sides. So we're going to multiply by 1/3 here, and times the 2 pi n. So we're going to multiply the angle out front by 1/3, and then we're also going to multiply the 2 pi n by 1/3. So we get x is equal to, and it's going to be pi divided by 12 plus, and when we multiply 1/3 times 2 pi n, we get 2 pi divided by 3 times n. And then here, we can cancel if we want before we actually multiply, so we can cancel the common factors of 3. So we get pi over 4 plus, and then here we multiply by 1/3, we also get 2 pi divided by 3 times n. Or you can write that as just 2 pi over 3 n. So here's all possible coterminal solutions for the actual angle x itself. Here we want to solve this equation for x, and x has to be over the interval 0 to 2 pi. So we have 2 times sine of x divided by 2 equals 1. This time our input angle is x divided by 2. This is our input angle, and we cannot change that. We cannot multiply the 2 that's on the outside of the function and cancel it with the 2 that's on the inside of the function. So we want to be careful there. The first thing I want to do is get sine of its input angle by itself on one side. So in order to do that, we want to get rid of the 2 that's out front. So we are going to divide both sides by 2. When we do that, the 2's on the outside will cancel, and we're left with sine of x divided by 2, and that's another way of saying half of x, equals 1/2. Now our goal is to solve for the value of the input angle. So we want to solve for x divided by 2. This is also the same thing as saying 1/2 times x. It's all the same. We want to solve for the input angle and figure out what angle, if I take the sine of that angle, do I get 1/2. And that's our 30-degree angle family, or the pi over 6 family. So when I'm looking at my unit circle, it's the pi over 6 family. Since we're talking about radians. And sine is also a positive 1/2 in quadrant 2, and that would be 5 pi over 6. So we have 5 pi over 6 and pi over 6. Let's write those. Go ahead and write those in. Okay. Well, before we do that, let's go back and look, where are we actually supposed to be solving for x divided by 2? So we're supposed to adjust our solution interval before we decide what the solutions for x over 2 would be. Well, the original interval for x was in between 0 and 2 pi, so let's write what that interval would look like in the form of an inequality. And what we're originally solving for is x between 0 and 2 pi, but what we have to solve for initially is x over 2. So if I go through and I divide everything through by 2, that tells me that I have to first solve for pi over 2, or x over 2, in between 0 and pi. So this is basically half rotation of the top half of our circle. So I only want solutions from the top half from 0 to pi. And that's what we have. We actually have two solutions where sine is a positive 1/2 at pi over 6 and 5 pi over 6. So we adjusted our solution interval, divided everything through by 2. So we're only looking for angles at the beginning here between 0 and pi. And we have our two angles from the top half of our circle. And now we actually want to go through and solve for x. So I don't want 1/2 x, or x divided by 2. What I want to know is, what does x have to be? So let's go ahead and rewrite what we have and then solve for x. So right now we have x divided by 2 is equal to pi over 6 and 5 pi over 6. We're going to multiply by 2, or think of it as 2 over 1. We're going to do it to both of the angles on the right hand side. So we get x is equal to, and if I multiply the top by 2, we get 2 pi over 6, and then 10 pi over 6, and we always want to reduce our solutions. So we get pi over 3, common factor of 2 here, we get 5 pi over 3. So we want to keep something in mind. The x values that we have are from the entire circle. So we were asked to originally solve for x between 0 and 2 pi. So the two solutions that we ended up with at the end are pi over 3 and 5 pi over 3, which is from the entire circle. Keep in mind that we originally solved for x over 2, or 1/2 x, just from the top half of the circle. Why would we only solve for x over 2 from the top half of the circle? Well, what happens is, when I want to actually solve for x, what do I have to do? Well, I have to double both of these angles. And if I take the original angles from 0 to pi and I double them, well, then I get angles that are twice as big. So I get an angle in quadrant 1, and this actually ends up over here in quadrant 4. So we actually have to double the angles. So if I solve for x over 2 in the top half of the circle, when I take those two original angles and I double them, then I end up with all of the solutions that I want from the entire circle from 0 to 2 pi. So when I take those angles and I double them, we end up staying in between the 0 and 2 pi that I wanted x to be within. Here we are asked to solve this equation for theta from 0 degrees to 360 degrees. So that means that when we get to the very end of the problem, the values for theta must range between 0 and 360. So we want to find all possible solutions for theta between 0 and 360. And all those solutions have to make this equation true. They have to balance out this equation. And we have theta over 2, or theta divided by 2, or 1/2 of theta, present in our equation. The first thing we want to do is we want to isolate or get cosine of theta over 2 by itself on one side. Now, in order to do that, we need to get those theta over 2's, cosine of theta over 2's together. So we're going to add cosine of theta over 2 to both sides. So now what we have is, on this side, we have two thetas that get added together. So that's two of those, 2 cosine theta over 2's equals, and now we have square root of 2. And we said we want to get cosine of theta over 2 by itself, so we need to divide both sides by 2. And now we have cosine theta divided by 2 equals square root of 2 over 2. All right, now we're solving initially for the values for theta over 2, and we have to adjust the solution interval. So initially when we're solving for theta over 2, we're solving for those angles. We're going to take the original interval and we're going to divide everything through by 2. So we're initially solving for theta over 2 in the adjusted interval from 0 to 180 degrees. In other words, a half rotation. So the top half of the circle. Okay, so what values, we're talking about the 45-degree angle family, what values from quadrant 1, that would be 45 degrees, and cosine is positive in quadrant 1 and then also in quadrant 4, and that would be 315 degrees. However, we are not going to use the quadrant 4 angle. According to our adjusted interval, we are only asked to solve for angles between 0 and 180 degrees, so just the top half of the circle. So we get 45 degrees as the only solution that we actually care about. Then the last thing that we're going to do is we're going to multiply both sides by 2 to solve for theta. And when we do that, we get theta is equal to 90 degrees. And that is actually the only solution that we care about for theta. Okay, why don't we care about 315 degrees? Let's talk about that. Because if I had written down 315 degrees, let's just explore that idea. If I had written down 315 degrees and I multiplied it by 2, that would give 630 degrees. Is 630 degrees in the allowed values for what we wanted to end up with for actually the values for theta? Well, the values for theta itself we said had to come between 0 and 360. Anything else outside of that interval we did not want to report as a solution. So this is outside of that allowed value, that allowed range. Here we are asked to solve this equation for all solutions. So there's not a specific interval that x has to be in. We want to solve for all possible solutions from the very beginning. The first thing we want to do though is we still want to get the trig function and its input angle by itself on one side. So in order to do that, we will divide both sides by 2 times the square root of 3. So we have sine of x over 2 is equal to 3 divided by 2 times the square root of 3. And we want to do a couple of things. The sine value looks unfamiliar, but we want to simplify this fraction. We want to rationalize, we want to get rid of the square root that's at the bottom. So we'll multiply top and the bottom by the square root of 3. And we know that square root of 3 times the square root of 3 is going to be 3, so that's really 2 times 3. And that gives sine of x over 2. That gives a common factor at the top and the bottom of the fraction. So we have 3 times square root of 3, 2 times 3. We're going to cancel out those common factors, and now we end up with a very familiar value for sine, square root of 3 over 2. And that is the 60-degree angle family, or the pi over 3 family. And let's go ahead and solve in radians since we have that x as our variable. So we're going to solve for x over 2 first, and we're going to solve in radians. So we're going to say on the unit circle, we said that was our pi over 3 family. And sine is also positive in quadrant 2, and that would be 2 pi over 3. So we want all possible solutions, which means I'm going to add 2 pi n, or 2 n pi, times both of those original angles. So we're going to add, so pi over 3 plus 2 pi n. And then the second solution from quadrant 2, 2 pi over 3 plus 2 pi n. Now the final step for solving this equation for all possible solutions is to actually solve for x. So step 1, we got sine by itself. Step 2, we solve for x over 2 for all possible solutions. And now we want to solve for x for all possible solutions. In order to solve for x, that means we have to multiply by 2. Think of it as 2 over 1 if we want. But that means I also have to multiply every term on this side also by 2. So not just the angle out front, but also the 2 pi in. So now we get x is equal to 2 pi over 3 plus, and we have 2 times 2 is 4, so that's plus 4 pi in. 4 pi over 3 plus 4 pi in. So this is all possible solutions for x in radians. Here in example 7, we're asked to solve for all solutions from the very beginning. So we don't have a specific interval for theta. We want to get the sine function by itself on one side. So we want sine, the trig function, and its input angle. And notice that the input angles here are exactly the same. We want to get sine 2 theta by itself on one side. That's our first goal. In order to do that, let's add sine of 2 theta to both sides. So when we do that, sines cancel out on the left side, and we end up with 2 equals 5. So we have 4 sine 2 theta plus 1 sine 2 theta. We end up with 5 sine 2 theta. The last thing we want to do is get rid of the 5 that's being multiplied times the front of the trig function. So we're going to divide both sides by 5. So our first goal was to get sine of 2 theta by itself. And now we have done that. The next thing that we want to do is we want to solve for 2 theta. Now we don't know exactly what this angle is, as far as the sine value that we're given is actually unfamiliar. So when we solve, we're going to solve using our calculator. We're going to put this ratio into the inverse sine function. Keep in mind that the sine function, the sine value is 2/5, that's positive, so we're going to be looking not only in quadrant 1, but also in quadrant 2. So the calculator tells us that 2 theta is equal to, and in my calculator I get 23 let's round to the nearest tenth, I get 23.6 degrees. So one of the angles from quadrant 1 is 23.6. Now we're asked to solve for all possible solutions, so we'll go ahead and add 360 times in. Now the other solution we want to look for is in quadrant 2, and it has to have a reference angle of 23.6 degrees. So what is that quadrant 2 angle? Well, we'd have to do 180 degrees minus 23.6. So the quadrant 2 angle that we are looking for is 156.4 degrees. Of course, we're going to add 360 in again. So we have all possible solutions for 2 theta. Now, we don't want to solve for 2 theta. In the end, we really want to get to what theta itself has to be. So we're going to go through and we're going to divide everything through by 2. So we're going to divide 23.6 divided by 2, that gives us 11.8 degrees. Plus, remember that we divide every term by 2. So not just the angle out front, but also the 360 in. So that's plus 180 in. And 156.4 degrees divided by 2, I get 78.2 degrees. Plus, and then we also divide 360 in by 2, which gives 180 in. So these are all possible solutions. That last step is to solve for all possible solutions for theta itself. Remember, divide everything through by 2, not just the angles out front, but also the terms that follow to give us those coterminal angles. Here we are asked to solve once again for all solutions, so all coterminal solutions from the very beginning. For this one, we want to look at the fact that we have our input angle is 2 theta. And we're going to go ahead and solve for all solutions in degrees. This one we have to be a little bit careful about because you see that it's cosine squared of 2 theta. Let's let 2 theta represent just an angle called u. So let's say that we have 2 times cosine squared of the input angle, which let's just call u for a minute, equals 1 minus cosine of the input angle, u. If we were solving this equation in section 6.2, we have a cosine function squared, and then we have a cosine function that's not squared. So these are not like terms. We have to be careful about that. And in fact, if you were to go back to the algebra, which is what we did in the last section, the algebra would look like 2 times, let's let this be like a cosine function squared, let's let that be like x squared, equals 1 minus, and this is just the cosine function not squared, so that would be like 1 minus x. If I was solving this equation in algebra, I would get everything over to one side, 0 on the other, and then I would try to factor. And that's what we're going to do here. So I'm going to bring everything over to the side with cosine squared, so I'm going to subtract 1 and add cosine of the angle. So minus 1 plus cosine of that angle u. So we get 2 cosine squared u plus cosine u, go ahead and put it in the order that we're familiar with, minus 1 equals 0. And we're going to factor this. So it's a trinomial, looks like 3 terms here. So we're going to do 2 cosine of u times cosine u. And then the only values we have for the last term would be 1 and 1, and we need opposite signs to get the negative 1. So let's put a plus here and a minus here. And that should give us the middle term that we want. Then, of course, once we factored it, we would set each one of the factors equal to 0, and then solve to get cosine u by itself on one side. So I would add 1 to both sides here, and then divide by 2. So we get cosine u is equal to a positive 1/2, and here, subtract 1 from both sides, we get cosine u is equal to minus 1. Now, u, what is actually u standing for here? Well, u stands for the original input angle, which we had as 2 theta. So 2 theta was the original. So I'm going to go ahead and just go back to the original 2 theta, so we can see what we're actually trying to solve. Cosine 2 theta is equal to 1/2. Cosine 2 theta is equal to minus 1. Now we are asked to solve for all possible solutions, so we don't have to worry about a specific interval for theta itself. So we're going to solve for 2 theta here. 2 theta, and we're talking about angles from quadrant 1 and quadrant 4 where cosine is positive, and that would be the 60-degree angle family. So we have 60 degrees plus all possible coterminal solutions, so we'll say 360 in. And then also in quadrant 4, where cosine is positive, talking about our 60-degree angle family, that would be 300 degrees. So 300 degrees plus also 360 in. Now we're not actually supposed to solve for 2 theta only, we're not supposed to stop there. Once we have solved for 2 theta, we're supposed to divide everything through by 2. So we get theta is equal to 30 degrees plus 180 times n. And dividing here by 2, we get 150 degrees plus 180 n. So divide everything through by 2. Here we have theta is equal to 30 degrees plus 180 n, and also 150 degrees plus 180 n. So we have 2 partial solutions. Now we want to find the last remaining solution for 2 theta. So we have 2 theta is equal to, and we want to know what value on the unit circle has a cosine value of -1. Now remember, on our unit circle we're looking for cosine values. That's the x values of the point that lays on the unit circle. So that would be 180 degrees that has a cosine value of -1. So we have 180 degrees. Now we're looking for all possible coterminal solutions, so we're going to add 360 in. And the last thing that we said we want to do is divide everything through by 2. So we get theta is equal to 90 degrees plus 180 degrees times n. So these are our 3 solutions that would give us all possible coterminal solutions for theta. In the last 2 examples, we will look at using the double angle identities to help us solve these equations. Here we have sine 2 theta is equal to sine of theta. Notice that the input angles are not the same. These are not like terms. So we have to be careful here if the input angles are not the same. It would be nice if the input angles were the same throughout the equation. Well, in order to get the input angles to be the same, what we can do is replace sine 2 theta with its equivalent as a double angle identity. So the double angle identity for sine 2 theta is 2 times sine theta times cosine theta, which is really nice because if we can replace cosine 2 theta with its equivalent, notice that within the double angle identity, cosine 2 theta is equivalent to 2 functions where the input angle is just theta. So now throughout the equation, the input angle is exactly the same for all of the trig functions. Now if we were solving this equation starting here, in section 6.2, we would get everything on one side, 0 on the other, and then try to factor. Now notice that when I get the 0, when I subtract sine theta from both sides, that these are not like terms. So I can't actually combine them, but they would just sit side by side. So that would be 2 sine theta cosine theta, and then minus the sine theta that we subtracted from both sides. Now we have equals 0. So we are attempting to factor here. And now we notice that there's a common factor between both of these terms. And we're going to factor out that GCF sine theta. So we're left with 2 cosine theta minus 1. And then of course, once we factor, we set each of the factors equal to 0. And then we have 2 equations that we want to solve for theta. So in the first one here, we have sine theta is equal to 0. So we're looking for values that have a sine value of 0. So on the unit circle, where do we have a y value of 0? Let's see, that would be at 0 degrees and also at 180 degrees. So if I look at both of those points on the unit circle, the y values of both of those points is 0. So here we get theta is equal to 0 degrees and also 180 degrees. Now we do not have to do an adjusted interval here because the input angle at this time is only theta. So here we want to solve for cosine theta, so I would add 1 to both sides and then divide by 2. And what 2 angles then would we be describing here? So we want cosine is a positive 1/2, and that would be the 60-degree angle family in quadrant 1 and then also in quadrant 4. So we get 2 angles for theta here. We get 60 degrees and 300 degrees. So we have 4 solutions, 0, 180, 60, and 300 degrees. So we want to look for opportunities here to use the double angle identity, and one of those clues is when the input angles throughout the equation are not the same. Here we want to solve this equation for x over the interval from 0 to 2 pi. So we're working in radians. And we want to first look at the input angles throughout the equation. And we notice that the input angle for cosine is 2x, while the input angle for sine is just x. It would be nice if throughout the equation we had the same input angle. In order to do that, we would have to look at cosine of 2x and use a double angle identity for cosine. Now, cosine has several double angle identities. Let's go ahead and write them all out and then pick which one would be the best. So cosine of 2x, the first one I think of is cosine squared x minus sine squared x. The next one that I think about would be 1 minus 2 times sine squared x. And then the last one, cosine squared 2 times cosine squared x minus 1. So these are our three double angle identities for cosine. Which one would be best to replace cosine 2x in this particular equation? Well, notice that on the other side we have the trig function sine. Not only would it be nice to have the input angle to be only x throughout the equation, but it would also be nice if we could pick the double angle identity so that the entire equation would be in terms of only sine. So I'm going to pick this double angle identity, and I'm going to replace cosine of 2x with its equivalent 1 minus 2 sine squared x. So now throughout the equation, the trig function is the same, and also the input angle is the same, which means we can bring everything over to one side and attempt to factor. So let's bring everything over to the right-hand side. It doesn't matter really which way you go, but I'm going to try to get my 0 on the left-hand side. So I'm going to subtract 1 from both sides, and I'm going to add sine 2 sine squared x to both sides as well. So I get 0 is equal to, on the right-hand side, as I bring all the terms to the right-hand side, I notice that 1 minus 1 cancels out, and I'm left with two terms that are not like terms, because one is squared and one is not. So I'll write positive 2 sine squared x minus sine x, and I am going to factor out a greatest common factor, which would be sine x. So I have sine x times 2 sine x minus 1 equals 0. And now that I've factored out my GCF, I'm going to set each one of the factors equal to 0. Now notice that since we use the double angle identity, we do not have to adjust the intervals because now all of our equations are already in terms of just x. So all we have to do is solve for x itself. So x is equal to, so we want to know where do we have a sine value of 0, and that would be at 0 radians, and then also at pi radians, since the y values of both of those points would be 0. So that's x equals 0 radians and x equals pi radians. So those are our first two solutions. And then we need to add 1 and divide by 2. So we get sine x is equal to 1/2. And on the unit circle, those two angles would be pi over 6 from quadrant 1 and 5 pi over 6 from quadrant 2. So we get 4 possible solutions here for x that satisfy the original equation. So we're going to be on the lookout for using those double angle identities if the input angles throughout the equation are not the same. And you want to be aware that there are other times when the other two double angle identities for cosine would be useful. And remember that we used the idea that throughout the equation we wanted to have the same trig function throughout, and also the same input angle. So sometimes it would be more beneficial to use this double angle identity if it could help accomplish that goal, and sometimes this one would be useful as well. So be on the lookout, make sure you know all three of those double angle identities for cosine, because either any of those three could be useful when using a double angle replacement for the equation.